So in this session, we will discuss the structure question related to topic acid-base equilibrium. In part C, the first reason why I skipped the first part, it is related to organic chemistry. That's the next topic. So acid dissociate constant Ka for a lactic acid is 1.3 into 10 to the power minus 4 mole per dm cube. Write an expression for dissociation of the lactic acid. The formula for the lactic acid. This is a lactic acid which is given. So when this lactic acid will dissociate, acids are proton donors, so it will donate proton. So it will be CH3CH OH in a bracket. Then COO negative will be there and H positive. So when we write the dissociation constant Ka, so writing a dissociation constant K, that is product divided by reactant. So product is the concentration of CH3COO, CH3. So it will be CH3 CH in a bracket OH and then CO NH plus and divided by the concentration of the reactant. So CH3 CH in a bracket OH CO H will be there. So this is the expression for dissociation constant of the lactic acid. Then state whether lactic acid is a strong or a weak acid than ethanoic acid. So how to work out whether it's a strong acid or a weak acid? For this, you have to use a data booklet and identify the value of the dissociation constant Ka. Like if it's having a higher value of a dissociation constant, then it will be strong. And if it's like lactic acid is having a higher value of dissociation constant than ethanoic acid, then it will be a strong acid. So when we check the dissociation constant for lactic acid is 1.38 into 10 to the power minus 4. Using the data booklet, we will work out the dissociation constant for ethanoic acid. So for ethanoic acid, this is ethanoic acid. The dissociation 1.7 into 10 to the power minus 5. So it means ethanoic acid is having a smaller value of a dissociation constant. The Ka of ethanoic acid is 1.7 into 10 to the power minus 5. So it means that does not dissociate too much, or it's having a smaller value of a K. It means ethanoic acid will be a weak acid and lactic acid will be a stronger acid. So you will mention here lactic acid will be stronger because it is having a higher value of K. Is it clear? Because it dissociate, as the substance dissociate more, the value of the Ka will increase because it will have more ions. So it has greater Ka or dissociation constant compared to that of ethanoic acid. The next, calculate the pH of 0.1 mole per dm cube solution of a lactic acid. So how to work out, as the value of the Ka is already given in the question, that was given in the beginning of the question, the part. 1.38 into 10 to the power minus 4, and we already use the expression for Ka. The expression for Ka is the Ka, or the dissociation constant. It is the product divided by reactant. The pH is 0.1. We need the pH, and the concentration of a lactic acid is 0.15. So what is our assumption here? Like we have CH3 CH is there, OH, and then COO. So CH3, CH, OH in a bracket, and then COH. It will dissociate into CH3, CH, OH, and then COO negative and H positive. In the beginning, the concentration will be 0.150. This will be 0 and 0. At equilibrium, if this is X, this will be 0.150 minus X. But we assume X is very small, so this will be approximately equal to 0. Like, because X is a very small value, so 0.15 is minus X is approximately equal to 0.15. Then we substitute when we write the expression, the dissociation constant is product divided by reactant. So product concentration at equilibrium X and X. So this will be X square divided by 0.150 minus X. We'll write 0.150. The value of the K is given 1.38 into 10 to the power minus 4. That is given in the beginning of the question. So we have the Ka, 0.15 will be multiplied and we'll take a root. So it will be 1.38 into 10 to the power minus 4 times 0.15 and take the root. So that will give us a value of X. And value of X is the concentration of hydrogen ion or concentration of the negative ion. And after knowing the concentration of hydrogen ion, which is approximately 4.5 into 10 to the power minus 3. So X is equals to 4.5 into 10 to the power minus 3. Then use the formula for pH. pH is equals to minus log of hydrogen ion concentration. So the pH is equals to minus log of hydrogen ion concentration. We substitute the hydrogen ion concentration here. The pH of the solution will come out as 2.35. Whenever you write the pH, you should use 2 decimal places. Then assumption, what is the assumption? State 2 assumptions. So not only one, the 2 assumptions what we made here. We assume that the initial concentration of the acid is same as the final concentration, like acid concentration does not change at equilibrium or initial. And we assume that the hydrogen ions are only coming from the acid, that like this hydrogen ion, because the acid and alkali are in aqueous solution, so water is also there. So water might also contribute to this hydrogen ion. So the amount of hydrogen ion will not be same as the amount of the negative ion, but we assume that water is not considering means contributing to hydrogen ion. So what are the two assumptions? Number one, the initial concentration of the acid or lactic acid is same as concentration at equilibrium. That is one thing. And the second one, the hydrogen ions are from acid only. Because sometimes what happens, the water molecule might also lose electron, so means lose proton or hydrogen ion in the solution, but hydrogen ions are coming from acid only. Is it clear? That's why we assume that both have the same value or X, otherwise practically it won't be same. Theoretically, yeah, it will be same because of our assumption.
So can we also just say that the negative ion concentration and H plus ion concentration is
Yeah,
the
you
same?
can mention that as well.
Okay.
But sometime like the ratio is 1:2, then it will be twice. But normally it's not like this, so you can use that. Another part, buffer solution is there, which is having a pH of 4. Is prepared by using a lactic acid and sodium lactate. A buffer solution is a weak acid and its salt, or weak alkali or its salt. So this buffer solution is prepared by lactic acid is a weak acid. Compared to ethanoic acid is stronger, but overall it is a weak acid. So a pH 4 is there. calculate the mass of sodium lactate that should be dissolved in 1 dm cube of 0.15 mole per dm cube solution of lactic acid to make this buffer solution. The pH of the buffer solution is 4 and sodium lactate has a molar mass of 112. So first what we will do, we will find the concentration of the, because again, whenever acid or alkali is there, weak acid, weak alkali, so there's always a dissociation constant, Ka is there. So Ka is equals to concentration of the salt CH3CH OHCO, because when you have this salt is there, this will dissociate into CH3 CHOHCO and plus Na. So the concentration of the salt will be the same as the concentration of this negative ion, then hydrogen ion divided by the concentration of acid, which is CH3CH OHCOOH. So first what we'll do, we have the value of the Ka, we have the value of the concentration of acid as I mentioned here. We have to calculate the mass of sodium that should be dissolved in 1 dm cube of 0.15 mole solution of lactic acid. So we have the concentration. We can also find hydrogen ion concentration. As we know, pH is equals to minus log of hydrogen ion concentration. So hydrogen ion concentration will be equal to 10 is power minus pH will be equal to the hydrogen ion concentration. So 10 is power minus 4 will be the hydrogen ion concentration. After knowing this, what we'll get the concentration. Okay. This because this is concentration. I will solve the question, but I'm explaining the idea. So after knowing the concentration is moles by volume. Volume is it's 1 here. So what concentration you will get, because concentration into volume will give us the moles. And after getting the moles multiplied by molar mass, you will get the mass in gram. So this is why it's a 4 marks. So moles multiplied by molar mass will give us the mass in gram. Is it clear, the idea, the concept?
Yes, sir.
So K is already given, that is 1.38. So K is already given 1.38 into 10 to the power minus 4. The concentration of the negative ion that we are finding, that's unknown. The concentration of hydrogen ion is 10 to the power minus 4 divided by um, concentration of the acid, which is 0.15. So we'll find this X, the concentration of lactate ion, that is 0.207 moles per dm cube. And then we have the concentration 0.207 multiplied by volume, we'll get the moles. So we'll get the same number because the volume is 1. So after getting the moles, so 0.207 multiplied by molar mass is 112. So how much mass in gram? 23.18 grams of sodium lactate is used to make this buffer solution. Clear? Then a small volume of hydrochloric acid is added to a buffer solution. Explain why the pH of a solution does not change significantly. Include an equation which you refers to. So whenever we add like
The H
acid,
plus ions react, yeah, with
yeah, yeah. So when we add hydrogen, the equilibrium is shifted towards left hand side for acid, or more molecules are formed. But the ratio, the important thing is the ratio. Like this is Ka is equals to concentration of the salt, concentration of hydrogen ion divided by concentration of acid. So the ratio, because the hydrogen ion, when we simplify this equation, we can say the hydrogen ion, the concentration of hydrogen ion is equals to Ka, the concentration of acid divided by concentration of the salt. So this ratio does not change, like because we have a reservoir, like we have a too much salt, even if one or two molecule of acid are increased, then it won't make difference to the final value. So it's of 3 marks. How you will score the 3 marks? So when we add an acid, the equilibrium will shift towards left hand side, and the points which you should mention: first thing, you will have a like large amount of lactate ion. So the hydrogen from hydrogen ion, H plus ion, or proton basically, because instead of hydrogen ion you can say proton from HCl react with lactate ion and shift the equilibrium towards the left hand side. But the ratio of acid, the concentration of the acid to the salt does not change. So if the ratio remain constant, then the hydrogen ion won't change too much, and that's why the pH will remain unchanged. So this is always the case that this ratio, even acid is added or alkali is added, but this ratio will remain unchanged. Now this question is about carbonic acid is a weak acid which dissociate in two stages. First stage, what happened? H2CO3 in the water from HCO3, and then SCO3 in water from CO3. The dissociation constant for the second value is smaller and the first one is higher. So it means H2CO3 is a stronger acid as compared to HCO3, because Ka value, this is -7, this is -11, so this is higher K, so means comparatively. So we have to write an expression for dissociation constant for A and first stage and second stage. So it is always a product divided by reactant. So Ka1, the product is, and this is a heterogeneous equilibria. Heterogeneous equilibria means when we have different states, we call that as a heterogeneous equilibria. So in heterogeneous equilibria, we don't include solid and liquid because their concentration is remain unchanged. So when we write here, so we'll write H2CO3. No need to include water because water is in a liquid state and their concentration in a liquid state does not change. Like solid concentration or liquid or concentration remains same in a heterogeneous equilibria. So we'll write HCO3. So this is the expression for dissociation for the first one as well as for the second one. Then in the question, a solution of carbonic acid has initial concentration of Ka. The initial concentration is 0.1. Ka1 is given, which is 4.17 into 10 power minus 7. Use Ka1 to calculate the equilibrium concentration mole per dm cube of hydrogen carbonate ion HCO3 ion and give your answer in 3 significant figure. So we have the value K is given and the expression which we mention here, that Ka1 is equals to H3O plus HCO3 and divided by H2CO3. So we assume originally it was, say, any number, as they mention here, it was zero point 0.1. So originally it is 0.1, this is 0 and 0, but at equilibrium x and 0.1 minus x, but x is negligible. So we can say original concentration of weak acid is same as concentration at equilibrium. So substituting the values, 4.17 into 10 to the power minus 7, H3O, that is x, this is also x, so x multiplied by x, it will be x square, and divided by original constant, it should be 0.1 minus x, but we assume that x is very small, so 0.1 minus x is approximately same as x. So this will be multiplied. So 4.17 into 10 to the power minus 7 times 0.1, and x multiplied by x is x square, so we'll take a root. This will give us a concentration of HCO3 ion at equilibrium. So that concentration, it will be 2.04 into 10 to the power minus 4. Then use your answer in B1, calculate the pH. So how we'll calculate the pH? Because what we assume here, that the concentration of oxonium ion is same as concentration of hydrogen carbonate ion. So this will be same as the concentration of oxonium ion, which is H3O. And this oxonium ion, what it dissociate? It will dissociate into water, and it will dissociate into proton. So amount or concentration of oxonium ion will be same as concentration of hydrogen ion, because the ratio between them is 1:1. So the concentration of hydrogen ion will be 2.04 into 10 to the power minus 4. Then we use a formula, pH is equals to minus log of hydrogen ion. So pH is equals to minus log of hydrogen ion concentration 2.04 into 10 to the power minus 4. This will give us the pH of this solution. So negative log of 2.04, this will give us 3.69, the pH of this solution. So pH will be 3.69. State 3 assumptions you made in calculating B1 and B2. Like B1 is there and B2. So what are the 3 assumptions here? Whenever we have a weak acid, we consider the original concentration is same as concentration at equilibrium, that is 1. And second thing, we consider that the proton or hydrogen ions which are there, it's only coming from the acid, it's not from the water. And the third thing, we assume, because when we calculate this, the last answer, that the concentration of H2CO3, but practically what will happen when H2CO3 convert into HCO3 and we got the concentration, but SCO3 will further dissociate into this. But we assume because HCO3 is having a smaller value of a dissociation constant, so it will not dissociate further. That's our assumption. So 3 assumptions here. The initial concentration of the acid, H2CO3, is same as equilibrium concentration. The second assumption is, we assume that the HCO3 minus concentration is same as H plus concentration, or H plus is only from the acid. And the third one, we assume that this HCO3 does not dissociate further.
Sir, can you explain the third one again?
Because what will happen when we calculate the value for HCO3, as you can see, That first H2CO3 will dissociate into HCO3, and then HCO3 will dissociate into CO3. So this H2CO3 dissociate into HCO3, and HCO3 further dissociate into CO3. So if the further dissociation will take place, the amount of the hydrogen ion won't be same, because this HCO3 will further contribute to protons. It will also donate proton. That's why the water is protonated here. Like H2O is there, become H3O. So it means this water also protonated. So if this happen, like first H2CO3 dissociate into HCO3, and then HCO3 further dissociate, then the amount of hydrogen ion in the solution will change. And as the amount of hydrogen ion in the solution change, the pH of the solution will also change. Is it clear?
Yes, sir.
Then in part C, carbonic acid form two types of salt. One is carbonate, another one is hydrogen carbonate. The solution sodium carbonate is titrated. A solution of sodium carbonate is there, Na2CO3 is titrated with HCl. On the grid sketch likely shape of a titration curve during the reaction. The carbonate requires 2 moles of hydrogen ion per molecule for a complete reaction, and 10 cm cube of sodium carbonate mixed with a concentration 0.1 is used, and sodium carbonate in the solution. The sodium carbonate solution is having a pH of 11.3, and 40 cm cube of hydrochloric acid of concentration 0.1 mole per dm cube is added. The pKa and pKa1 means when the first acid is formed, that's pKa1, and the second acid is there, that is pKa2. Like it's the same thing. Ka1 is there, so using a Ka1, we'll get pKa1, and using a Ka2 dissociation constant, we get pKa2. Clearly label any equivalence point in the sketch. So the reaction, a solution of sodium carbonate is titrated with the hydrochloric acid. So we have what? We have a solution of sodium carbonate, Na2CO3. Okay. This Na2CO3 solution will dissociate into what? It will dissociate into sodium plus and carbonate minus. This carbonate, what is the possibility that this carbonate can accept proton, like it can accept one proton from water. When we check the reverse reaction, the two equations are given. So this carbonate can accept proton from the water. We have H2O. So if it accepts proton from the water, as a result, what will form? It will form HCO3. So as a result, what it might form? It will form HCO3 and OH. This is one. Or second thing, what is the possibility? That this HCO3 will further react with water, and it will form H2CO3 carbonic acid plus second OH. So both possibilities are there. It might form HCO3 minus, or it might form H2CO3. So why the solution, when carbonate ion is there, why the solution is alkaline? Because the carbonate ion has a tendency to accept protons. When something accept proton in the solution, will have more OH ion. That's why the solution of carbonate salt will be alkaline. So what we are doing, we are titrating the carbonate salt solution with hydrochloric acid, and because of the carbonate salts, the carbonate ion, the solution will be alkaline. It will have a tendency to accept proton. That's make a solution alkaline. As I mentioned here, you can see that the sodium carbonate solution has a pH of 11.3. So why the sodium carbonate solution is having a pH of 11.3? because the carbonate ion is having a tendency to accept proton from the water molecule. So it increases the amount of OH ion. As the amount of OH ion increases, the pH will also increase. So, and there are two possibilities. It can either accept like one proton, like first it accept proton from one water molecule. So it will form HCO3 minus. The solution will be alkaline, and then it can take another electron, proton from the water molecule, from another water molecule, which further increases the pH. So two dissociation constant are there, like as you can see, pKa1 is there and pKa2. What is the meaning of pKa1? It means that this is a moment when this ion HCO3 ion is CO3 ion is reacting. Here, as you can see, the SCO3 ion is reacting because the one, so when we have HCO3, because the one which is having a smaller value of a Ka, the pK will have a higher pKa because they are inversely proportional to each other. So we can say pKa is equals to minus log of Ka. So the one which is having a higher Ka will have a smaller pKa, and the one which is having a smaller Ka will have the higher pKa. So we have to complete this sketch. How we will complete the sketch? The volume of hydrochloric acid added. So two things are there. Because this hydrochloric acid HCl is there, it, so we have in the beginning sodium carbonate, Na2CO3 is there. This Na2CO3 will dissociate into sodium plus charge and carbonate minus charge. And this carbonate, if it accepts like one water molecule, then it will form HCO3 minus and OH. HCO3 is there because it is accepting protons, and OH is also minus. And then this HCO3 ion further reacted with water, so it will form H2CO3 molecule plus another OH. So these are the two stages, but we can write in collective, like if maybe possibility is there, if carbonate might reacted with two water molecules. So as it react with two water molecules, as a result, it will form HCO3 plus 2 OH will be there. So what is the ratio? If the HCO3 is formed, what is the ratio? What will be the ratio between HCl and OH? The ratio is 1:1 because one molecule of HCl will react with one molecule of OH. But if H2 carbonate ion reacted like mixed with two water molecule, then it produced two OH. So what will be the ratio of HCl to OH? The ratio will be 1:2. So if we have the equal concentration of the two solutions, we have the equal concentration of carbonate solution. So if the first reaction occur, we need the same volume. But if the second reaction occur, we need the volume twice. Like we need the volume of hydrochloric acid for the second reaction twice as compared to the first reaction. So in the beginning, sodium carbonate 10 cm cube is there. So if I have 10 cm cube of sodium carbonate, how much HCl is needed for this reaction? The first reaction, I need 10 cm cube. But if the second reaction occur, if we have 10 cm cube of sodium carbonate, how much hydrochloric acid is needed? 20 cm cube of hydrochloric acid is needed, as the ratio between the hydrochloric acid and OH ion is 2:1. Like if we have 10 cm cube, the total this will be 20. So the HCl will also require 20 cm cube. So there will be two equivalence point and it will start at 11.3. So this is 8, 9, 10, 11. So this number is 11 and 11.3 will be somewhat here. So it will start at 11.3 and there will be two vertical lines, one around 10.3 because PK, so one is about 10.3, so 8, 9, 10. So one is around 10.3 and another one, it's a weak acid, a strong acid and weak base. So whenever a strong acid and weak base, they are reacting with each other. The vertical region is from 7 to 4 to 7 or 7 to 4 if you are going in this way. So 7 to 4. So when we join these points, starting from 11.3, this this shows that because some of the carbonate ion might accept one proton from water, so it produces one OH and these OH are being neutralized by 10 cm cube of HCl. But then most of them, as carbonate ion has a tendency to accept two protons, so most of them will produce two OH ions and we need twice the volume. That's why the volume of hydrochloric acid will be twice. And then hydrochloric acid is a strong acid, so it will end at pH 1. Is it clear that equivalence point will be there at 20 and 10? Yes, Hashim. Is it clear, this part? So propanoic acid is a weak Bronsted Lowry acid. Determine the term Bronsted and Lowry acid. So acids are proton donors. So we can mention it donate proton. Then what is a pH of 0.1 mole per dm cube solution of hydrochloric acid and how would the pH of any weak acid of same concentration differ? So the pH is equals to minus log of hydrogen ion concentration, and we assume that the concentration of acid is same as concentration of hydrogen ion. As a strong acid, they ionize completely. So it will be minus log of 0.1. That will give us the pH of pH to be 1. And when we compare this with other weak acid of same concentration, so they will have a higher pH because they are not ionizing completely. Then methanoic acid was mixed with propanoic acid. Use a data booklet to decide which is strong. So how methanoic acid and propanoic acid data booklet is there. Methanoic acid is mixed with propanoic acid. Methanoic is 1.6 Ka and propanoic is 1.3. So it means methanoic acid is having a higher value of Ka. So methanoic acid comparative, both are weak acid, but in comparison, this is strong and this one is weak. So, and how we say both are weak acid, because for strong acid, we don't write a dissociation constant as it ionizes completely. So the ions are more and so it will be like infinite, very high value will be there. That's why for strong acid, we don't write. So weak acid we write. And in this case, methanoic acid is having a higher value than propanoic acid. So methanoic acid will be strong acid, because the one which is having the higher value of Ka, it means it dissociate more or more ions are there in the solution. So methanoic acid is stronger compared to propanoic acid. Then when two acids are mixed together, what will happen? The strong one will lose proton. So we have methanoic acid and propanoic acid. We know comparatively methanoic acid is stronger. So always remember the strong one will lose proton. So it will form HCO, and the other one will be C2H5COO H2, and the charge will be positive because this is having a higher value of a Ka methanoic acid, so it dissociate more and it increase the amount of hydrogen ion in the solution. Calculate the pH of a solution, 0.5 mole per dm cube sodium hydroxide. So how to work out the pH? Dissociation constant is given for strong alkali and base. Because sodium hydroxide is a strong base, so we consider that the concentration of the base is same as the concentration of hydroxide ion. So if it was 0.05, this will be 0.05. So Kw, the dissociation constant for water, or dissociation product for water, product of H and OH. So we have Kw, which is 1 into 10 power minus 14. We have hydrogen ion, we don't know, but we have OH, which is 0.05. So after getting this value for 0, so 1 into 10 power minus 14 divided by 0.05, this will give us a concentration of hydrogen ion. And the concentration of the hydrogen ion, we'll get the pH. The pH is equals to minus log of hydrogen ion, so we'll get the pH of this solution. Then a buffer was made. So a buffer was made by mixing 20 cm cube of 0.05 sodium hydroxide with 20 cm cube of 0.5 mole of propanoic acid. Write an equation for reaction between sodium hydroxide and propanoic acid. The concentration of propanoic acid is more than concentration of sodium hydroxide. So we have the formula that like the reaction between propanoic acid. So prop means 3 carbon. So CH3, CH2, COOH reacted with sodium hydroxide, NaOH. So as a result, sodium will displace this hydrogen. So it will form CH3, CH2, COONA, sodium propanoid plus H2O. State symbols are not required, but acids are aqueous, alkali aqueous, salt aqueous, and water is liquid. Calculate the pH of this buffer solution and refer the data booklet. Why we need a data booklet? Because we need Ka value, dissociation constant. But first, as this is an equation, so we should know the moles, like how many moles are left. And always, whenever you are making a buffer solution of strong acid and weak acid and its salt, or weak base and its salt, so either weak base or weak acid will be left, and the alkali or the acid which is stronger will be used up. So here, sodium hydroxide is a stronger alkali, so it will be used up. So first we'll find the using a concentration and the volume, we'll find the moles of sodium hydroxide. So before we mix 20 into 0.05, the moles of sodium hydroxide, as this is 20, and divided by 1000 as well, as the concept volume should be in decimeter cube. So the moles for sodium hydroxide, and the beginning, that is 0.001, and moles of Propanoic acid concentration into volume, concentration is 0.25, volume is 20 cm cube divided by 1000, so it will be 0.005. The ratio between them is 1 is to 1. So the ratio is 1 is to 1. If this is a limiting reagent, so it will be used up, and 1 is to 1 is a ratio, 0.001 will react. So how many moles will be left? 0.004 will be left. And how many moles of salt are produced? The moles of salt is same as the moles of the alkali used. The ratio is 1 is to 1. So it will also produce 0.001 moles of the salt. And about the water, here the same amount will be there because the ratio is 1 is to 1. But we don't need for water. Now this is the moles, but to get the concentration is mole divided by volume. We mix 20 cm cube in the beginning. We mix 20 cm cube of acid with 20 cm cube of alkali. So new concentration will be mole divided by new volume, which is 40 cm cube, or divided by 1000, so 0.04. So this will also be 0.04. So that will give us the concentration of propanoic acid. The concentration of propanoic acid 0.004 divided by 0.04, so it will be 0.1 mole per dm cube, and the concentration for this one, it is 0.025 mole per dm cube. Now we'll use the expression for Ka, or hydrogen ion concentration is equals to Ka, concentration of the acid divided by concentration of the salt. So this will give us the hydrogen ion concentration Ka. We already checked from the data booklet, it is 1.3 into 10 to the power minus 5. The concentration of the acid is 0.1 and the concentration of salt is 0.025. This will give us the amount of hydrogen ion, the hydrogen ion concentration, and after knowing the hydrogen ion concentration, we'll calculate the pH. That pH is equals to minus log of hydrogen ion. So it is approximately 4.28. Is it clear, this question? That how we work out the
Yes, sir.
pH of a buffer solution? So for buffer solution, you will find these type of questions common. Explain how this solution act as a buffer when small amount of alkali is added, include any relevant equation. So if we add an alkali, buffer solution changes or resists a change in pH. So first we have a reservoir or large amount of the conjugate base or propanoid ion in this one, and when we add alkali, that will react with hydrogen ion, like the proton from hydrogen ion, so equilibrium will shift and more protons will be produced. But the ratio between the salt and the acid does not change, as we have a reservoir. So the points which you will include, we have reservoir, propanoid ion, according to relevant to the question, because like propanoid ion is coming from the salt, it is also coming from the acid. Then what will happen? Addition of the alkali shift the equilibrium. Addition of alkali uh, cause reaction between high H plus ion and OH minus ion, which shift the equilibrium towards the right hand side, because if amount of hydrogen decrease, equilibrium shift towards the right. But as a result, what happened? The ratio of the concentration of acid to the concentration of salt hardly change. So the amount of H plus ion remain constant, and as the amount of H plus ion remain constant, the pH won't change. Is it clear? This question? So it's a similar way. So the next session will do more questions from this topic, as it is a very important topic from the syllabus content. Any question related to the class today?
No, sir, it's clear.
Okay, so I'll end the session and share this with you.